Okay, so in this video, I'm going to prove to you guys that the derivative of ln is 1 over x. The background on this one is kind of wild, and there's a lot of log stuff involved here naturally because we're dealing with logs. So let's go ahead and look at our background here really quick. Something that I do mention in my classes, either in Algebra 2 or pre-calculus, is the following interesting fact. If you take this expression, 1 plus 1 over n to the nth power, and you take the limit of that as n approaches infinity, you get a very special number out of that. You get the letter e, which is 2.71 approximately. That's Euler's number and something that we talked about. Now, for the sake of this proof, what's going to happen is we're going to end up with an expression that looks a lot like this, but it's going to be slightly different. So let's go ahead and see what that's going to look like. So what I'm going to do here is I'm going to do a little u substitution to change the way this looks, so it's going to look the way it's going to look when we actually end up doing our proof. I'm going to say that u is equal to 1 over n. Okay, now one thing that we can derive from that is if we do some cross multiplication here, that means that n is equal to 1 over u. So I'm going to come over here and I'm going to replace these numbers here. 1 over n is u, so I'm going to put a u here, and n is 1 over u, so I'm going to put a u there. I'm just doing u substitution. It doesn't change the value. It just changes the way it looks. So this whole thing's still going to equal e. You'll notice that I didn't put in approaching over here because we also need to do something with that. Since I'm changing it to u, we also need to know what u is approaching. Well, if 1 over n is equal to u, then if I take the limit as n approaches infinity on both sides, I end up with the following thing. We know from calculus that this equals 0. So the limit of u as n approaches infinity is 0. And what that means is that as n is approaching infinity, that's the same thing as u approaching 0. Okay? So, once again, this is background stuff. In your proof, you can honestly just jump straight to this. You don't need to demonstrate all these things to me. I'm just trying to explain them to you. But let's go ahead and also look at a few other interesting things that we need to remember about when we're doing this proof. That's one thing you're going to want to be aware of. Here's another thing. As you guys might recall, that if you have log A plus B, no, I'm not doing that right, sorry. Back up a little bit. If you have log A minus log B, then that can be rewritten as log A over B. We are going to make use of that fact. Another log rule is that if you have a number, I'll call it n, being multiplied by a log, then you can rewrite that as log, but with that number being a power on the a, the arguments in that case. So those are going to be a couple of the things that you're going to want to remember as we go ahead and take on this proof. So remember, my goal here is I'm trying to prove that the derivative with respect to x of ln of x is 1 over x. Okay? So let's go ahead and begin. So we start, of course, by taking the limit as delta x approaches 0 of ln of x plus delta x minus ln of x all over delta x. Now, The first thing I'm going to do is I'm going to apply one of my log properties here. Okay, if you have two logs being subtracted, you can rewrite that as one log where those arguments are being divided. So what that's going to look like then is the following. Next thing I'm going to do is I'm just going to do some simple algebra here. First of all, instead of having a delta x on the bottom, dividing by delta x is the same thing as multiplying 1 over delta x. So I'm going to rewrite it like that. So I took this delta x and moved it out to the side, right? So now I have just 1 over delta x times ln. And on the inside, I'm also going to simplify this a little bit. If I divide the x into the x, I get 1. And if I divide the x into the delta x, I end up with delta x over x. So now what was the point of moving this delta x over here to the side? Well, now it's a multiplier, and I can apply another log rule. The log rule I want to apply is the one that says that I can take this multiplier and make it an exponent. So I have the following. Okay. All right. Well, so this expression here should start looking pretty darn familiar, and it should. We're working our way there, so we're gonna keep going. Now we're gonna do something very similar to what I did at the beginning with the background here. I'm going to replace x over delta x with u. So I'm going to say that u is equal to delta x over x. That way I can replace this with a u, so it looks more like what we had in our beginning of our background. But if I'm going to be replacing all the delta x pieces with a u, I need to fix this one too. So I need to figure out what delta x equals. If u is equal to delta x over x, then delta x by cross multiplication is equal to u times x. Okay? So if I do my u substitution there, I end up with the following. Okay? But as we did in the background thing as well, I don't want delta x here anymore, right? We need to figure out what is u approaching as delta x is approaching 0, because I need u to be approaching something if I'm going to be redefining everything in terms of u. So let's go ahead and figure that out. So right now, if I have u is equal to delta x over x, if I let the limit of this as delta x approaches 0, then we can figure out what this is. Now, the x is not affected by this entire thing, just the delta x. So the delta x is approaching 0. So what I end up with is just 0 over x by direct substitution, and that's 0. So that means that the limit of u as delta x approaches 0 is 0, which means that as delta x approaches 0, u approaches 0. So I actually have the same value I'm approaching there for both of those. So there's that. And now we're going to do some more math magic here. We're getting close. A few more steps. First of all, I'm going to rewrite my log a little bit. Not my log, but actually the exponent. I'm going to rewrite it like this. Okay? So I'm going to, instead of having 1 over u times x, I'm going to rewrite it as two separate fractions, 1 over u times 1 over x. And then what I'm going to do is I'm going to apply that log rule, but in the backwards fashion now. Instead of taking a number in the front and moving to the power, I'm going to take it from the power and move it back up here to the front. So it's going to be the following. Now, we are ready to go ahead and start doing the limit here. First of all, this limit does not affect the x. The x has nothing to do with the u. It's not defined in terms of u whatsoever. But I do need to apply the limit as u approaches 0 to this piece here. Now this is a composite function here, right? So what I'm going to do then is when you have a composite function, is you take your limit and you put it inside the function, right? So we're going to be finding the limit as u approaches 0 of this expression here. That was a rule we talked about with limits a while back. When you have a composite function, a function inside of a function, you're taking a limit of it, you apply the limit to the inner function. Okay? And so this is something we talked about in our background. What does that equal? That equals e. And ln of e is 1. And therefore, the derivative of natural log is 1 over x. All right. So that is our proof for the derivative log.